All right, let's dive in. Today we're going deep on a topic that, well, the name's a bit of a head scratcher.
It is, isn't it?
We're talking about inadequate NMR spectroscopy.
You see that name and you kind of wonder what you're getting yourself into.
Right. It's not exactly inspiring confidence, is it?
Not really.
But, appearances can be deceiving, right?
Absolutely.
We got a ton of articles from you guys about
Oh,
this.
yeah.
And let me tell you, my curiosity is piqued. I'm really intrigued to see what this is all about.
Well, good.
So, to start us off, can you give us a quick rundown on what NMR is all about?
Yeah, so NMR in general, it's like giving scientists this incredible X-ray vision. But at the molecular level, it's how they see what these tiny little building blocks of matter actually look like.
Right, molecules. I remember that from my chemistry days, way back when.
Yeah, exactly. And the structure of a molecule, how the atoms are all arranged. That's super important because it determines how that molecule behaves, how it interacts with other molecules.
Okay, so that makes sense.
So NMR helps us figure out those structures, kind of like making a 3D blueprint of a molecule.
So, where does this inadequate thing fit in?
Well, it's a spiralized type of NMR. Instead of showing all the atoms, inadequate zooms in on the carbon atoms and how they're connected to each other.
Okay, so it's mapping out the carbon skeleton, kind of like the backbone of the molecule.
Yeah, precisely.
That's got to be pretty important for understanding how a molecule functions as a whole, right?
Oh, absolutely. If you think about it, that carbon skeleton, it's the framework upon which everything else is built. By knowing that exact arrangement of carbon atoms, scientists can start to understand how a molecule interacts with its environment, how it might react with other molecules, and even how it might behave in a biological system.
So it's not just about seeing the individual pieces, it's about understanding how they fit together and how that influences the bigger picture.
Exactly. It's like, you could have all the pieces of a puzzle, but without knowing how they connect, you'll never see the whole picture.
Right. So how about we dive into how this inadequate thing actually works? But maybe keep it simple for us non-scientists out there.
Okay, fair enough. So inadequate relies on this special form of carbon called carbon-13. It's a little bit different from the regular carbon we usually find.
Different how?
Well, most carbon atoms are what we call carbon-12. They're stable and abundant. But carbon-13, it's like the rare cousin. Only about 1% of all carbon atoms are carbon-13.
Okay, so it's a rare bird.
And the cool thing about carbon-13 is that it has this unique magnetic property that makes it really sensitive to NMR. Carbon-12, on the other hand, is pretty much invisible to this technique.
Uh-huh. So inadequate specifically targets those rare carbon-13 atoms.
Exactly.
I'm already sensing a challenge here, trying to work with something that's only 1% of the total.
Yeah, you're definitely on the right track there. Now, here's where it gets a bit mind-bending. Inadequate uses two dimensions to show those carbon-carbon connections, kind of like a graph.
2 dimensions. I'm intrigued.
So imagine a map,
Okay, I'm picturing a map.
and each X on the map marks the spot of a carbon-13 atom. And by analyzing the signals, scientists can draw lines between those X's to see if the carbon atoms are directly connected.
Wait, so it's literally like a molecular connect the dots.
You got it.
That's wild. But I bet those maps, or spectra as you call them, must be pretty complicated to interpret, right?
Well, they can be, yeah. That's where the real expertise comes in. Scientists have to look at the position, intensity, and shape of each signal to decipher those connections.
So it's like a code they have to crack.
Exactly.
This is starting to make me wonder if maybe they called it inadequate, because finding those rare carbon-13 atoms and then interpreting those complex spectra must be a real headache.
Yeah, well, the name definitely reflects some of the challenges involved, and one of the biggest hurdles is that sensitivity issue. Remember, we're working with a very small percentage of carbon-13.
Right, just that 1%.
So it's like trying to hear a whisper in a crowded room. You need incredibly sensitive instruments and a lot of patience to pick out those signals.
Wow, okay. So inadequate might be an understatement, but I'm guessing scientists wouldn't use this technique if it was truly hopeless, right?
You're absolutely right, and that's what we'll explore in part two.
Okay, so even though this technique has inadequate in its name, there must be some situations where it really shines, right? Like where it's worth all that extra effort.
You're absolutely right. It's like any tool, really. You wouldn't use a hammer to screw in a light bulb, would you?
No, probably not the best tool for the job.
Exactly. So inadequate, it's not the go-to for every situation, but there are certain scenarios where it's absolutely invaluable.
So what kind of scenarios are we talking about? When does this technique really become the hero of the story?
One of the big ones is when you're dealing with really complex molecules, especially those with a lot of carbon atoms that are kind of all in similar environments.
So, like, if you were using regular carbon NMR, it would just be this jumbled mess of signals.
Yeah, exactly. It would be like trying to find a needle in a haystack.
Okay, I can see how that would be a problem.
And that's where inadequate comes in. Because it focuses on those direct carbon-carbon connections, it cuts through all the noise and gives you a much clearer picture of the overall structure.
So it's like having a map instead of just wandering around aimlessly.
Exactly. And a very precise map at that. It pinpoints each carbon atom and shows you how they're all linked together step by step.
That's pretty impressive. So it sounds like inadequate is the tool of choice when you absolutely need to know the exact carbon skeleton of a molecule.
Precisely. No other technique can provide that level of detail and certainty.
And why is that so important? Can you give us some real-world examples?
Sure, let's take drug development, for instance. When you're designing a new drug, you need to know exactly how that molecule is structured, because even tiny changes in the arrangement of atoms can drastically alter how a drug interacts with the body.
Right, so it's not just about having the right ingredients, it's about having them arranged in the right way.
Exactly. And inadequate helps scientists make sure they've got that structure absolutely right, which is crucial for safety and effectiveness.
Okay, so that makes sense for pharmaceuticals. But what about other fields? Where else is inadequate making a difference?
Oh, it's used in a wide range of areas.
Hmm.
Material science, for example. Researchers use it to design new materials with specific properties.
Like what kind of properties?
Well, think about the materials used in aerospace engineering. They need to be lightweight, yet incredibly strong. And to achieve that, you need to fine-tune the molecular structure very precisely.
I see, so inadequate is playing a role in shaping the future of technology. That's pretty cool.
It is, isn't it? And all this from a technique with such a, well, a less than flattering name.
I know, right? But earlier you mentioned that scientists have come up with some clever ways to overcome that sensitivity issue, like enriching the sample with extra carbon-13. Can you explain how that works?
Sure, it's actually pretty straightforward. Basically, they're increasing the concentration of carbon-13 in the sample.
So it's like giving inadequate a boost,
Yeah.
making those signals easier to pick out.
Exactly. It's like turning up the volume on that whisper we were talking about earlier.
Okay, that makes sense. And I'm guessing they use other tricks too, right? To make those carbon-13 signals stand out even more.
Oh, absolutely.
Hmm.
They use much more powerful instruments with stronger magnets that are able to detect even those faintest of signals.
So it's a combination of clever sample preparation and cutting-edge technology.
Precisely. And those advances have really expanded the possibilities of what inadequate can achieve.
That's great to hear. But I'm curious, are there any downsides to these approaches? I mean, there's always a trade-off, right?
You're right, there always is. And one of the big ones is cost. Those super strong magnets we talked about, they don't come cheap.
So not every lab has access to that kind of equipment.
Unfortunately, no. And even with carbon-13 enrichment, it can still be a pretty time-consuming and expensive process.
Right, so there are practical considerations as well.
Definitely. And it's worth noting that even with these sensitivity boosts, interpreting those inadequate spectra, it can still be a challenge. It requires a lot of experience and expertise.
So you really need to know what you're looking at.
You do. It's like deciphering an ancient language.
I can imagine it gets pretty frustrating at times, but I'm guessing the insights you gain are worth all that effort, right?
Oh, absolutely. Because those insights can lead to some truly remarkable discoveries.
Like what? Can you give us some examples?
Sure, one area where inadequate with carbon-13 enrichment is really making waves is in the field of metabolomics.
Metabolomics. Now remind me again what that is.
Well, it's basically the study of all the chemical processes happening inside a living organism.
Okay, so it's looking at the big picture of how molecules interact and transform within a cell.
Exactly. And by enriching certain molecules with carbon-13, scientists can use inadequate to track their journey through those metabolic pathways.
So it's like giving those molecules a tracking device and following their movements.
You got it. And by analyzing those carbon-13 connections, we can start to understand the incredibly complex web of chemical reactions that drive life itself.
Wow, that's mind-blowing. We've gone from mapping out drug molecules to understanding how cells function, all thanks to this technique called inadequate.
It's pretty amazing, isn't it?
It really is. I think it's safe to say that we've officially debunked the myth of inadequate NMR.
I think so too.
But before we get too carried away, there's one more fascinating aspect of inadequate that we need to explore, and that's how scientists actually interpret those complex spectra. How do they extract meaningful information from all those peaks and signals?
That's a great question, and that's exactly what we'll delve into in part 3.
Okay, so we've talked about how inadequate helps us map out those carbon skeletons, even in the most complex molecules. We've even seen how scientists are using it to track the flow of molecules within living cells.
It's pretty remarkable, isn't it?
It is. But I have to admit, I'm still a bit mystified by those spectra, those maps of carbon connections.
Yeah, they can be pretty intimidating at first glance.
They really can. So, for our final deep dive here, can you walk us through how scientists actually make sense of those spectra? How do they go from these abstract signals to a concrete understanding of a molecule structure?
Well, it's a process that requires a lot of skill and experience. You see, each signal in an inadequate spectrum represents a connection between two carbon atoms.
Right, like those X marks on the map we were talking about earlier.
Exactly. And scientists have to carefully analyze each signal to figure out what it's telling them about that connection.
So, what kind of information are they looking for?
Well, one of the key things is the position of the signal. That tells them something about the chemical environment of those two carbon atoms.
The chemical environment.
Yeah, like what other atoms are nearby, what kind of bonds they're forming, things like that.
Okay, so the location of the signal gives them clues about the surrounding neighborhood.
Exactly. And then there's the intensity of the signal, how strong it is. And that can tell them something about the type of bond between those carbon atoms.
So, a stronger signal means.
Well, it could mean that those two carbon atoms are connected by a double bond rather than a single bond, or maybe even a triple bond.
Uh-huh. So the intensity is like a measure of the strength of that connection.
Exactly. And then there's the shape of the signal, which can tell us even more about the surrounding environment and the dynamics of those carbon atoms.
So it's like each signal is telling a story, and scientists have to piece those stories together to understand the whole picture.
Precisely. It's like solving a puzzle, but instead of pieces, we're working with these signals, these clues about carbon connections.
I'm starting to see why it takes so much expertise to do this.
It does. Scientists have to use their knowledge of chemistry, physics, and even a bit of intuition to decipher these spectra.
And I imagine it can get pretty complicated, especially when you're dealing with a molecule that has dozens or even hundreds of carbon atoms.
Oh, absolutely. Sometimes those spectra can look like a tangled mess of peaks and signals. It can take days, weeks, even months to fully analyze a complex spectrum.
Wow, so patience is definitely a virtue in this field.
It is, but the rewards are definitely worth it. Because when you finally crack the code, when you see that molecular structure emerge from all that data, it's an incredible feeling.
I bet it is. It's like uncovering a hidden treasure.
You got it.
So even though it has this name, inadequate, it's clear that this technique is anything but inadequate.
I agree. It's a testament to human ingenuity,
Mm.
our ability to come up with ways to probe the world at the most fundamental level.
And it's a reminder that even though science can be complex and challenging, the insights we gain are often truly groundbreaking.
Absolutely. And who knows what the future holds for inadequate? With new technologies and approaches being developed all the time, the possibilities are endless.
Well, on that note, I think we've reached the end of our deep dive.
I hope you enjoyed the journey.
I certainly did. And I learned a ton. So to all our listeners out there, thank you for joining us on this exploration of inadequate NMR.
And remember, even though the name might sound a bit negative, it's actually a powerful tool that's helping us unlock some of the most fascinating mysteries of the molecular world.
And as always, thanks for listening to The Deep Dive.